G'day, my name is Brendan. This is the third part in a series of videos on mpstat. In this part, I'll take a few select columns and I'll show how you can do further analysis using tools such as dtrace. I've logged into a live system that's running a variety of workloads, and here's the summary since boot, but what I'll do is I'll get mpstat to run with the 1 second interval. So just looking out for a few things that are interesting to analyze, I've got some CPU cross calls that are happening. I see that's running on CPU 7 at the moment, but it's moving around. We've got a reasonable amount of spins on kernel mutexes that I can analyze as well. And if I watch for long enough, there is an issue I mentioned in an earlier part where one of the CPUs does go hot. There we just caught it. A CPU went to 100% system time. It's intermittent, so it'll be a bit tricky to chase down, but one of the advantages of mpstat is you can look at how balanced the CPUs are, and it's identified that issue. So I'll show you how you can find that. Also, this looks pretty interesting. So CPUs 13 and 14 have a higher rate of interrupts than the others and are doing more system time than the others on average. So I've just mentioned a few interesting things from the output of mpstat. So let's go and use tools to dig deeper. I'll start by using dtrace to have a look at these CPU crosscalls. And dtrace gives us a couple of providers which are excellent for investigating the mpstat columns in more detail. One of them is sysinfo, and I can see from this output there are various probes, including pswitch for context switches. There's a probe for CPU crosscalls. Another provider which helps explain the mpstat output in more detail is the vminfo provider. But here I'll use the sysinfo provider. I'm going to use the xcalls probe. And what I'll do, I'm just going to run a dtrace one-liner that, and I won't go into too much detail of dtrace, but it instruments CPU crosscalls, and it's going to do a frequency count of the kernel stack backtrace so that I can find out the reason why we're doing CPU crosscalls. So I'm going to run this for a few seconds and then hit Control-C. In the other window, I've still got crosscalls happening. So this shows the entire stack backtrace. At the bottom, it is the count of how many times that stack backtrace led to that probe event. That probe event was the crosscalls. And by reading from bottom up, I'm going up to ancestry. This is read kstat data. And then we're going into VM-free, hat unload, hat TLB inval. So this is the hardware address translation layer. We've got TLB for translation, look-aside buffer. This is part of how the operating system manages memory from the virtual to physical address space. And this is a cache coherency type of crosscall. I'd expect looking at this stack backtrace here. Of course, I can go and read each of these functions if I've got access to the source code to understand that in more detail. Just scrolling up, this one here, same thing, hat TLB inval. This one's actually coming from a stack backtrace of exec common gexec. This looks like it's from executing a new command. And that may be part of, at a guess, I would have to do a little bit more dtrace, but as a guess, this may be part of the natural fork exec sequence where fork has initially referenced the other address space, but we're now invalidating it and populating it with the new executable code that we're going to run. Here, this is a hat TLB inval, and this is coming from exit. So a process is exiting, and it's cross-calling the other CPUs to say that those pages are invalid. So scrolling up, I can see that pretty much all of these are in hat TLB inval. So we're invalidating some TLB entries. That's cross-calls for memory management. What I can do is I can also use dtrace to find out the processes that were causing them as well by adding the exec name to that one-liner. So dtrace can help drill into this in more detail to find out why we're doing crosscalls. It looks like we're executing processes. What I'll now do is look at one of the other interesting columns. I'll pick on SMTX, which is the spins on kernel mutexes. To analyze this, we can use dtrace. We can instrument the mutex locks using probes directly, or we can use a tool called lockstat, which does it for us. Lockstat in Solaris 10 onwards is dtrace based, but it did exist before that. And let me just fire up lockstat. I'm not going to go into too many details of lockstat. Lockstat's very powerful. It's also, since it's instrumenting the locks and it's using dtrace for that, even though the overhead of dtrace is very light, since locks are accessed so often, they're accessed many hundreds of thousands of times a second or millions of times a second, that overhead can add up. So that the performance impact while running lockstat can be noticeable. Here I've run it so I've said sleep 5. With lockstat, it will execute a command and then finish when the command exits. So this is just a quick way I can get lockstat to only run for 5 seconds. The other options I used, generally on busy systems I need to increase the data buffer count. Minus S8 will give me 8 levels of stack backtrace. So this will run for 5 seconds. It'll output to a file. You don't need to do that, but the output is generally many pages long. And I can now read this file to find out what those spins were. It has a lot of really cool detail in a summary for each of the locks that you've been spinning on. So this is showing adaptive mutex spins. This is a distribution plot. If you've used dtrace a lot, this might look very familiar. This did predate dtrace and inspired the dtrace distribution plots. What we've got is the number of times that we were locked or spinning for that lock, and it shows the time. So in order to read this, this says 1,106 times we were waiting between 512 and 1,024 nanoseconds for this lock here. That was the caller, and that's the stack backtrace. Some of the locks will have symbol names, and I'll tell you what they are. This one doesn't. The stack backtrace we can read to understand the location of the lock. This is in the TCP routine, TCP send data, STR mdata fast path put, we're in the MAC routines, and then IGB, which is a network interface. IGB-TX for transmit. So this is a lock that's part of how the IGB network device driver does transmit. If this was getting too hot, this may tell me to go and investigate IGB tuning. It may have a configuration file. I may be able to tune exactly how it works and relieve pressure on that transmit lock. And the output of this goes through all the other locks that we were spinning on as well. So that's how you can get more information on that column, which is spins on mutexes. It's lockstat. Lockstat does bring some performance overhead when you're running it, but you can gather some excellent information in a short amount of time to find out exactly where those hot locks are. So some of the other things I wanted to go through included the interrupts. So these two CPUs are running with a high number of interrupts compared to the others. And I mentioned in one of the other parts that this is usually because a physical device is bound to those CPUs. And that device will interrupt the CPUs when they have work that needs to be processed. And often it's network interfaces. To investigate it in more detail, again, I can use dtrace because there's probes that let me look at interrupt processing. There's also a command that uses dtrace called intrstat. And let me just run that. intrstat with an interval of 1. Here I've Control-C'd it. It's listed out all the CPUs on the system. So CPU 0, 1, 2, 3, 4. And then the devices which are interrupting those CPUs. Now the ones we're interested in are CPUs 13 and 14, which are running at a higher rate of system time than the others and a higher rate of interrupts. And if I scroll down to CPUs 13 and 14, I can see that they are processing IGB2, which is a network interface. And CPU 14 was spending 43% of that interval servicing interrupts for that network interface. Another way you can figure this out, apart from using mpstat, is MDB, the modular debugger, MDB minus K, so that you can look at the kernel. There's a variety of D commands you can run in here. ::interrupts minus D lists out the drivers and then the CPUs they're bound to interrupt. And I can look down this list to see who's bound to interrupt CPUs 13 and 14, and I can see it right there. IGB2, 13 and 14, which is what we confirmed with ntrstat. So that's getting more information on interrupts. The other things I noted that were interesting to investigate included why sometimes a CPU was hot. So if I let this run for a few seconds, let's see if we can see it. So sometimes the idle time, there it was. I'll Control-C and scroll up. So during this second, one CPU was hot 100% in system time, and that sounds like a misconfigured application that should be multi-threaded so that it can run across multiple CPUs. I say should. Sometimes it can be advantageous to run on a single CPU because you're hot in those CPU caches. But anyway, this sort of output, which shows a vast imbalance, is worth investigating. Unfortunately, since it is intermittent, so there I think it was running on CPU 8, it is a little tricky to investigate. It's moving around, it only happens sometimes, and I don't think it's happening on the same CPU all the time. So how can we see this? Let me just feed this into awk. And this is field, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here I'm saying only print out a line if field 14 is greater than 99. It's printed out the text lines as well. So there you go. We were hot on CPU 4. Now it's on CPU 8. I just wanted to demonstrate that this problem is moving around. This is a problem that I may be able to use prstat to identify. Prstat minus ML for microstate accounting, C for don't clear the screen, N for number of lines to output, let's just say 3. prstat by default will sort on the CPU time. And what I can see here is, in fact, I do want it to output every second, so let me give it an interval. If there is a thread that goes, so there's a thread, HTTPT was 100% in user time. That's not the problem we're looking for. That's something else, actually. So that sounds like that web server needs some tuning. I'm looking for a thread that's 100% in system time, and there's one right there. So I caught IPMI tool 100% in system time for that 1 second interval. What Solaris likes to do is to keep threads on CPU for its CPU affinity so that it keeps the caches hot. So that's at least one of the reasons why we have this. There's another reason I just want to catch. And obviously when I'm doing live demos, it doesn't like to cooperate for me. Oh, no, it's actually IPMI tool. I was going to blame RCAPD, which is another process that can go hot on CPU time. And we see RCAPD floating up, but it actually looks like IPMI tool is the guy that is particularly 100% system time. Okay, there I've caught an RCAPD that's 100%. RCAPD 100% in system time. I previously knew that one was capable of it. I now have something new to investigate that I discovered while doing this. Okay. I mentioned dtrace can do this as well. Let me just give you a quick one-liner. Let's say I profile at 101 Hertz. And I'll frequency count the process name, process ID, and thread ID to get a unique identifier. And I'll print output every second. And I just control seed because there's what I'm after. I'm sampling at 101 Hertz. And this output is showing me the process name, the process ID, the thread ID. I needed those two so that I can have a unique identifier per thread, and the number of samples that it was on CPU. And I caught IPMI tool was on CPU for 101 samples. So if the operating system hasn't moved it around multiple CPUs, during that 1 second that I was printing, it was hot. A different way of doing this, if the CPU was fixed, which in this case it's not, but so for example, I could say only profile, which is sampling for CPU 8. And unfortunately, this problem was moving around, but that's a different way of investigating it. In fact, if I add the CPU identifier to the previous output, then I can definitely confirm that it was on one CPU for that entire time. So I'm looking for a count of 101. And there we go. I just caught RCAP-D. RCAP-D, process ID, thread ID, and CPU ID is 10, CPU 10, 102 samples. So it was, and it's a little bit off 101 because of scheduling of the dtrace command to fetch the aggregation buffers and print this out. But there I've identified one process, one CPU, hot the entire time. That's showing the occasional hot CPU. So I've now shown how you can use other tools to investigate the CPU cross-calls, the spins for mutexes, investigating interrupts in more detail, and looking at a particular hot CPU or unbalanced CPU. Thank you. Please note that some of the tools I just demonstrated are not currently available from within a joint Smart Machine or a Solaris 10 zone. That includes Logstat, INTRstat, and the dtrace VM info provider. If you are on one of these environments, you may still get benefit from the existence of these tools, as the administrator of the host can use them to investigate performance issues.